combination. So it looks like here you have kinetic energy terms, and then now in the potential energy term, now you have two terms. One is this Josephson junction with this cosine phi, and then the other one is this EL, and then there's a phi squared term. So you have combination of these two parts, and then so the name of the game that we're playing with the fluxonium is like you play in this particle in a box physics and then design the box. And then also you can also design the mass of the particle that put it in there. So for example, if I put the two extreme parameters limit, which is, for example, here EL is much more larger than EJ, then basically this parabolic terms is more important compared to this cosine term, then your potential more or less looks like this potential part. But because of this modulation of this cosine, then it's not exactly parabolic, so the eigenstate it's not equal spacing. So this can be achievable. The other part, the other extreme is like if you make the EL much more smaller than the EJ, then this cosine term become more important, and such that now you have like a potential looks like this. And the eigenstates are, well, you can see it's spread it in a very different way compared to this limit. Okay. So actually, the name of the game is again, it's just a play with these EJ, EC, EL. And so therefore, we have this periodic table that have been proposed in 2013 in the science paper, such that the ratio of EL and EJ and EJ and EC are just decided what kind of qubits that you are having. And so one of the important things associated with these parameter, ratio of these parameter also associate with how they sense, how are these qubits sensitive to various different noise. For example, if you on this left-hand side right here, if your EJ over EC is getting to the bottom right here, then it's less sensitive to the charge noise, and which is, for example, the transmon is less sensitive to the charge noise. That's and the way you put it, it's put a larger capacitor. And so fluxonium is about right here, and so actually it is also compared to the flux qubits, it's more or less sensitive to the flux noise. Okay. All right. So let me just now focusing on just the transmon and the fluxonium qubits. And so these are the potential of the transmon. You already see it. For the fluxonium, an important thing is that because here you form a loop for the superconducting qubit, for the supercurrent, because these inductors and the Josephson junction, you can have current flowing through. And actually you can thread it with the external magnetic field, and such that you're adding this external phase of that. And so therefore, if you're changing this external field across, or external flux that penetrates through this loop right here, you're able to change the potential also. And so this is an animation showing that with a different phi external, then you're able to change a different potential with the landscape of this potential. And then you will have a very different eigenstates of these fluxonium qubits. So one of the let me just focusing on one of the position that people love to use is this phi external equal to pi, which is sometimes we call it half-Earth quanta. And so at this region, so now you have these two like a local whale, such that they can form the eigenstate. Originally they are degenerated, but because of you can tunnel through this barrier, so they have the energy here will be splitted a little bit. And so with that, actually at this half-Earth quanta right here, the 0-1 transition typically is with a low frequency, okay? But all the other states, now you have some other states that are going to, for example, it's in the same whale. So this transition will go with a much more higher frequency. So by just seeing that, now the fluxonium actually, because of this potential landscape engineering, you're able to have a pretty large anharmonicity, which is very different from the transmon. And also because of you have like an interwhale transition or intra-whale transition. So the selection rule for the fluxonium is more engineerable. Okay. So here are some of the number that let me just put it in. So typically transmon qubits, the transition frequency, typically people set it around 4 to 8 gigahertz, but because of the potential can be changed very differently in fluxonium, so there are frequency can be like a 10 megahertz and even go to 8 gigahertz, so 8 gigahertz is at the integer flux quanta. And the enharmonicity is for the transmon is typically 200 to 300 megahertz, but for the fluxonium it can be like as large as 1 gigahertz. And the transition spectrum for transmon is more simple, but in the fluxonium it's quite rich. So this is one of the first, the very first realization of fluxonium superconducting qubits by my postdoc advisor Vladimir Manichayan in Yale. And so at that time, so this feature right here, you have a small junction shunted with these with the array of Josephson junction array. So this is a large inductors, and the capacitance is just being supported by the capacitance of the Josephson junction, and then so this is the readout resonator, and so this is the effective circuit, such that this part is the one that you see, and then so you capacitive coupling to a readout resonator, and then so you will be able to do the readout. Okay, and so here is the first realization of the spectrum of the fluxonium as a function of external flux bias going through penetrate these loop right here. And so indeed you can see that the spectrum is more rich, and then it's more tunable with these external flux. So later in the Maryland, what we have is we make these fluxonium in the like a 3D cavity, so that we can specifically tuning up the fabrication condition for the fluxonium qubit and make it simpler with this 3D cavity. And so this is an image of SEM image of enlarged fluxonium qubit and on top of a silicon substrate. Okay, and so you can see that these are the Josephson junction array. So a lot of people are afraid of these kind of Josephson junction array because the fabrication looks like a very, very hard. But actually, as long as you have like a good parameter for making these Dolan bridge, this yielding rate of these Josephson junction is quite high. So it's not that hard. And so this is the small Josephson junction that we made in here. Okay. So actually, there's one more things that you can more engineer with these fluxonium is, well, if you make these with this potential, actually we can use the same trick that the people make with the transmon, such that make this EL extremely small, which means that you need to put it with a very, very large inductors, and then also at the same time you make this EC really, really small, EC really large, which means the capacitance is really small. So this kind of a qubit, well, we call it Blochnium. So what will happen is because you make these parabolic turns really spread it out, and then so it's like the curving up is very, very slow, and because of the mass, which is the inverse of these EC, is really, really small, and so we call it kind of like in the light. It looks like a light particle in this potential, and so the wave function is spread it in these various cosine potential right here. And so with that, actually, then you can make a qubit that less sensitive to the flux noise. So in the past, we make these kind of qubit in this way. But you see that in order to make this EC small, we first want to make all these substrate that been etched out by dry etching, and then so such that the stray capacitance can be small enough. And then we even have these this Josephson junction array just peeled off from the substrate, but somehow it works. And so we measure these spectrum. So the 0-1 spectrum actually is quite flat in terms of external flux bias. And so and actually if you go into higher and higher transitions, then this transition frequency is changing as a function of, it's more significant, changing more significant as a function of external flux. And so this is actually just kind of like the x-axis is the charge bias for the transmon. So the 0-1 transition is insensitive to the external charge.